This first section, we're going to talk about antennas. Is my audio strong enough?
Yep, loud and clear, Steve. 5x9.
Okay. You see the radio, the transceiver generates the signal and decodes the radio signal. But the function of the antenna is it's the transducer between the electrical voltage and current coming from the radio and the propagation medium, which is the atmosphere. So an antenna has electrical contacts, but its output or input is a radio wave. The basic antenna, the most basic antenna, is a dipole, a half-wave dipole. And there's it's used to model all kinds of antennas. This one happens to be a half wavelength long, which gives it special properties. Bill, can you hear me now?
Yeah.
Okay.
Yeah, that was a while back, Steve. That was
Okay.
a while ago. Yeah.
All right.
You're coming through really loud and clear.
All right. The most basic antenna is a half-wave dipole. You see this has, it's a quarter wavelength long on each end. And this thing here is the feed line, goes to the transceiver, and there's voltage and current that comes up the feed line and gets on the antenna, and that creates an electromagnetic field. But again, the horizontal dipole, it's used as a measuring stick for all kinds of antennas. This is the basic antenna. Oh, come on now. Now, the direction of radiation for this dipole is the strongest broadside to the antenna, like coming right out of the screen. Coming off of the ends, it's at a minimum, but we graph the strength of the radiation in something called an antenna pattern, and that's what this is. In this particular pattern, the dipole is running along the 90 to 270 degree axis. And if I were to walk around this big circle at a fixed radius here, and I would measure the strength of the energy coming from the antenna, and I would plot it, it would plot like this figure 8. And again, like I said, off the ends of the dipole, there's not much radiation, but broadside it is a maximum. So again, that's another question. Which direction has the strongest signal? And it's broadside to the antenna, to the dipole. And again, the direction of radiation is strongest from a half-wave dipole antenna is broadside to the antenna, which is what I just said. And again, the antenna is a half wavelength long. Now, there are formulas for antennas, but a 6-meter antenna, you can just memorize this number, is 112 inches. But just think for a second, if a wavelength is 6 meters, then a half wavelength is 3 meters. And that's about 120 inches. And the multiple choice test that asks this question would have several choices, but only one of them would be close to 100, or would be close to 120. So you can memorize this number, but again, if you start getting worried about it, just take a deep breath and say, wait a minute. If the wavelength is 6 meters, then half a wave is 3 meters, and a meter is about 40 inches. So that's 120, and so 112 is close to that. There's a more exact formula to this too, but I don't see that in the questions. Now, if you make the dipole shorter, then it's going to resonate at a half wavelength still, but it'll be a half wavelength, a shorter half wavelength, which means a higher frequency. Let's pause for a minute here. The shorter the frequency, or the higher the frequency, the shorter the wavelength. Okay. So, and you talk about an antenna resonating. Resonance gives it particular properties, but in this the dipole resonates at a half wavelength. So if you want to make it resonate at a higher frequency, remember, as frequency goes up, wavelength gets smaller, or it goes down. So you shorten it. That's how to remember this. Now, this is a quarter wave antenna, a quarter wave vertical. But if you look, you see one end, this is basically a half wave dipole where you've bent the one end and added four other wires. This is a quarter wave antenna. The radiating element is a quarter wave, and it works against these things. They're called radials. They're the same length as the driven element. But you see, again, what do you got here? You got a half wavelength of wire. And at 146 megahertz, that's on the 2 meter band, right? And 2 meters is about 80 inches. And a quarter wave, a 1/4 of 2 meter of 80 inches is about 20 inches or 19 inches. So again, that's an easy way to do it. But again, this is a vertical antenna, very common, and it works against these guys, these radials, which form what's called a ground plane. Now, a directional antenna is an antenna that focuses or concentrates the transmitter's energy in one particular direction. Or if you are receiving, it listens better in the one direction where the energy is focused. You can, whatever you can say about an antenna transmitting is also true in receiving. So a direction, figure if you're going to, you can, and it can be more convenient sometimes to think about transmit, other times to think about receive. But thinking of a transmitting antenna, you want to focus it in a particular direction. That makes it a directional antenna. And there are ways to make an antenna directional. So if you have a blockage along your line of sight path, you can use a line of sight path means the direction you're looking towards the receive station. If you can't see the receive station, what you can do is think like on a pool table. If you're shooting a ball and there's something in your way, what do? You shoot it off the side rail to bounce around it. That's exactly what you do here. You can use a directional antenna to find a path that reflects signals off of something when you're trying to get to a distant repeater, but your path is blocked by buildings or obstructions. So you bounce a signal, nuts. Sorry, I hit the little roller on my mouse is what happened. So you bounce a signal off of a nearby building, like we said. Now, there are antennas, the degree to which an antenna focuses a signal compared to like a dipole is or some reference antenna is called antenna gain. You can make your transmitter very effective in one direction if you have a directional antenna that focuses in that direction. Now, there's an antenna called a Yagi antenna. Dr. Yagi was a Japanese professor in the 1920s, and he had a graduate student named Uda. And this particular antenna is properly called a Yagi-Uda antenna. But the Yagi antenna is very common, and it offers the greatest signal gain. Now, this particular antenna is called a quad or a cubical quad. The proper name is a cubical quad. This particular antenna is a Yagi antenna, and then this is a dish antenna. So the question that this is addressing talks about which antenna offers the greatest gain, and it talks about antennas like a vertical antenna or other ones we'll get to. But the Yagi is the one that's directional. And the way the Yagi works, this is not on the test, but this middle element is driven by the transmitter. See this thing here? And these other elements are not connected to the transmitter, but this particular driven element excites energy in these elements that adds up in such a way that it's highly directional to the right. So that's a Yagi antenna. It kind of looks like a TV antenna, and that's similar to the way some TV antennas work. The beam antenna concentrates signals in one direction. Here's the pattern, a Yagi radiation pattern. And again, if I were to walk around the antenna at a constant distance and make measurements, I would plot this particular graph. And in this pattern, the biggest lobe here is called the main beam, just like the beam of a flashlight. But there's energy that comes off the sides and the back, and these are called minor lobes. Back lobes and side lobes are minor lobes. And the E plane refers to the plane in which the conductor is. In this case, it's a vertical antenna. So in the vertical plane, which is the E plane for this is the pattern you would measure.
Hey, Steve.
Yes.
Joe here with a quick comment. And I apologize, Steve. I looked this up really quick while you were going through the other slides, and I just didn't get to it very quickly. For everybody on the line, Steve earlier was talking about the length of antennas, and there are questions in the test about that. And I just want to let everybody know that according to the, to the question bank, the formula for that to figure out the length of a half-wave dipole antenna, the simple equation for that is you take 468 and for everybody, if you do have a pad of paper, if you're taking notes, you may want to just jot this down. We will cover it in more detail, later on at Cramfest. But the formula is 468 divided by the frequency in megahertz. So, for instance, for a 40-meter dipole that is operating at 7 megahertz, you would take 468 and divide it by 7. And if you do that, you'll get 66 feet plus some change. Of course, if you wanted to convert that to inches, you just multiply that number by 12. But I just want to, and Steve, I apologize for jumping in, but I did just want to clarify because there are some questions in the exam pool about that. And that is how you calculate that for a half-wave dipole. Again, the formula is 468 divided by the frequency in megahertz. And if you have to then convert something to inches, you would just go ahead and multiply that by 12.
And that gives you a half wavelength in feet. Thank you. Thank you for adding that. That gives you the half wavelength in feet, and a quarter wavelength, of course, would be half of that.
Yeah.
I did look in the exam pool I did not see any, I saw 112 inches for a 6 meter half wave and 19 inches for a 2 meter quarter wave, but that's all that I saw. I'm glad.
Yes,
I'm
those
glad.
are the two questions, and you're exactly right, Steve. Those are the two questions that are in the question bank. I just wanted to let everybody know about how they came up with those numbers.
Yeah, that's how you do it. When I was an engineering student, we had a joke we'd always say, another letter that represents frequency is the Greek letter nu. You say, hey, what's new? And you say c over lambda. C is the speed of light and lambda is a wavelength. Anyway, engineer joke. What's new? C over lambda. But that's the way to remember it. But that's a rabbit trail. I will stop talking about that now. But yeah, 468 over F will give you the thing in feet. Now, what I was talking about is you can also remember the approximate wavelength, and the numbers on the exam, three of them will be way out of range, and one of them will be, the right answer. And the rule of thumb I was using also is another way to do that. But the right way is 468 over the frequency. Now, you can use a directional antenna to locate sources of interference or jamming using direction finding equipment. That's a receiver and a directional antenna, and you point the antenna different directions, and you listen in the receiver or you look at a meter, and it will peak when you've found a signal that you are looking for. So to locate sources of noise or jamming, you use radio direction finding equipment. Sometimes if you got power line noise, there's guys that walk along the power lines pointing at the power lines looking for a bad insulator with an outfit like this. We also, for practice, have something called a fox hunt, where the fox is a little transmitter we hide, and we look for it with directional antennas. So a directional antenna would be useful for a hidden transmitter. That's also called fox hunting, and that's on the test. In fact, after the Ham Fest, we usually do a fox hunt, and that's what we're doing. Now, we were talking about antenna gain, and that's the increase in signal strength in a particular direction compared to a reference antenna. Always compared to a reference antenna, and that's referred to antenna gain. See here, an isotropic antenna, that's a 50-cent word that means the same in all directions. Isotropic, or isotropic, I guess. Imagine a light bulb in the middle of a paper lantern like this. Every place on this sphere will be illuminated with the same amount of power per square foot or square inch. And that's the characteristic of an isotropic antenna. It radiates the same in all directions. Now, if you have a directional antenna and it focuses the antenna, so you get a stronger signal in one direction, is compared to what? Well, compared to an isotropic antenna. So the gain here is dBi. The I stands for isotropic, D stands for decibels. That's a logarithmic measure, but the gain of and it's 10 times the log of the high power to the reference power is what a decibel is. But gain in dBi is decibels reference to an isotropic antenna. You can also see it in dBd, which is reference to a dipole. But this question is talking about dBi being the reference. And let's see. Yeah, antenna gain, again, you always got to have a reference. It's the increase in signal strength in a specific direction compared to a reference antenna. Now, there's another kind of antenna, a vertical antenna, where the vertical element, instead of being a half wavelength long, is 5/8 of a wavelength. And that's used in VHF and UHF mobile service. It gives you a little more gain than a quarter wave vertical, and at a lower angle as well. It offers a lower angle of radiation and usually gives you improved coverage. So here you have, again, an antenna pattern, again, and the antenna is vertical in the middle here. And you see the quarter wave vertical is also called a monopole instead of a dipole because it's only got one radiating element. But here you see the pattern for a quarter wave vertical compared to a 5/8 wave vertical. The 5/8 wave has 3 dB more gain than the quarter wave at the horizon, and a lower angle as well, a lower radiation as well. See, the outer ring is a gain of 8 dBi. That says that a 5/8 wave vertical has a gain of 8 dB over isotropic, whereas the quarter wave has it like 8 minus 3 is 5 dB over isotropic. So this is an elevation pattern over a perfect ground. Here's the ground for quarter wave and eighth wave vertical monopoles. Now for long distance, you see for mobile, let me back up. Mobile stations, if you're in your car, you don't have much choice, and you usually almost always use a vertical whip antenna. So mobile stations use vertical polarization, but stationary antennas use horizontal polarization. What does polarization mean? Well, polarization is the direction of the electric field. Again, a radio wave is made up of electric and magnetic fields. The polarization is the direction in space of the electric field. And if the electric field is horizontal, it is said to be horizontal polarization. And the electric field runs the same direction as the metal in the antenna. So that Yagi antenna we saw earlier happened to be vertical, so that would be vertical polarized. If you rotate it so that the elements are parallel to the earth, that's a horizontal antenna. And that's what you use for weak signal, CW, and single sideband contacts. So the question is very simple, but a horizontal antenna polarization, it paraphrases this, is used for long distance CW and SSB contacts at VHF and UHF. Now, you see that here we have a vertically polarized signal. This would be if you could stop time and then walk along the radio wave, this is what you would measure. You would see the signal varying in a vertical direction. And see, the antennas are vertical. And then horizontally, this is horizontal polarization, and the electric field would vary this way. And again, you see the electric field runs the same direction as the metal in the antenna. There is a physical reason for that, but I'm not going to muddy the water. But if you try to receive a horizontal antenna or a horizontal signal with a vertical antenna, you're not going to receive very much. The receive and transmit antennas have to use the same polarization. And again, there's a physical reason for that. If your signal can be much weaker, significantly weaker, if the antennas at opposite ends of the line of sight link aren't using the same polarization. Okay, in this case, it said that they're cross-polarized. So if they're not the same polarization, you're not going to pick up as much of the signal. That's for VHF, UHF line of sight. Now, sometimes you can't, when you're trying to make an antenna, you can't get it long enough to be like a quarter wavelength, like at some of the lower frequencies. So there are tricks that you can use to make the antenna longer electrically than it is physically. and that's called loading. So a type of loading, when you refer to antenna, is where an inductor is inserted in the radiating part of the antenna to make it electrically longer. That's called a loading coil. And it kind of makes sense. You have the antenna and you add electrical length to it with this coil. This is called a loading coil. And here's our loading coils. And again, this is done because the antenna, you can't make it as long as you'd like to physically. So you add a loading coil to make it electrically a half quarter wavelength or whatever length you need. Also, adding capacitance on the top of the antenna, this is called a capacitive top hat, that also makes the antenna electrically longer. There's a physical reason for that as well. The capacitive top hat couples to the ground, and antenna radiating current actually flows up through the top hat and through the capacitance to the ground, which makes the antenna electrically longer. And that's the end of the antennas. Are there questions at this point? Okay, then I shall move on.